And hello again. Welcome back to the channel. We'll be now going over sort of the next steps. So let me just bring this bad boy up and we can take a look. So yeah, found out your audio reverb because of the new place and where the desk is, but we'll get that sorted. I think I've improved it a little bit, but we'll see. We'll give it a go. I might increase the volume once, see if that's okay. Probably not, but you never know. The next step we'll be going over is really just what is a byte. Again, very basic stuff. So, without further ado, we'll now go forward and discuss how computers store information. And from there, if I bring this a little lower for you, there you go, there you go, there you go, boys, there you go. Yeah, be fine. I don't know. I really should do this before. Yeah, that works. That works. Um, I should be fine. But we'll go over how computers store data, and that's stored in bytes or bits if you want a bit more pedantic. So let's begin. Let's move that up. Let's move this further up to the right. There we go. Now that'll be fine. So, okay, which one is it? Let me just draw something and see if that comes up. No. Okay, it's not this one. So, let's go over. So, how we store information is normally in letters, depending on your language, but for me it's English, it's A, B, C, D, or E, or it's the numbering system, which is the decimal system. But of course, back in the day, computers did not have a lot of space. You couldn't put decimalization. It seemed like a bit of a luxury. At the same time, letters, again, also quite a luxury. So computers needed a way of storing information as efficiently as possible using as little space as possible. And that was the introduction of the bit, which would eventually become the byte when it's composed of things, once it's all brought together. So if we took a look at our system, let's go at 999. We have the decimal system. So that is 100, 10, and of course 1. Because of course 10 to the power of 0 equals 1. Don't know why. It's just maths, crazy shit. Don't worry about it too much. But of course, that's a lot of space. You got to take into account all of that. You got to translation, all that sort of stuff. It takes too much time. So what the computer geeks did is they introduced the idea of a bit. So a bit is the smallest storeable sort of unit of data in a computer, and it uses a base 2. So we use a base 10. It just uses a base 2 system. So if you've seen The Matrix or seen, I don't know, the Big Bang Theory, then you would understand that the zeros and ones, and of course it can either be a 0 or a 1. And that is how computers store data. So this is the base 2 system. But of course, there's lots of numbers. You can't just explain everything with just a 0 and a 1. You can't just explain letters in a 0 and a 1. So what they did is then they added the bits together. So a bit is just 1, 0, or 1. A nibble is 4. And a byte is 8. 8 bits. 1, 2, 3, 4, 5, 6, 7. Let's put another one here. 8. And so what happens is the computers and the system basically creates or uses mostly bytes to store data, which is about 8 bits. And if the data is larger, then they might use more than one byte. And then you end up with more and more bytes. So we'll go into more complexity about this later. But for now, the smallest bit of data on a computer is a bit, which then, of course, the smallest usable bit of data is normally a byte. And most computer systems and most data are stored in bytes. You can also have a word, which is actually 16 bytes. No, 16 bits, which is 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8. and that becomes a word. But this is a small, useless sort of information that, that will be a bit useful later. And then you've got your byte here. But we have to understand that there's more than zeros and ones in the world, and multiple letters. I mean, if you could only use 0 or 1, it'd be an A or B, or 1 or 2, 0 or 1. And so what these smart chaps did is they effectively broke it down into a base 2 system, but with each bit representing a certain value. So if we go 1, can you see that, boys? Yeah, 1, 2, 3, 4, 5, 6, 7, 8. We now have 1 byte, or 8 bits. This is then broken down. So it's a base 2 system. It can either be a 0 or 1. 1 being on and 0 being off. And then each bit has its own representative value. So at the start we could have 1, so 2 to the power 0 equals 1. And of course, if that's ticked on, that means that this bit equals 1. Next one will be 2, 4. It keeps on going up in 8s because it's the base 2 system. 16, 24. Can you guess the next one? Times up by 2, 32. Whoa, I'm an idiot. I'm an absolute idiot. Basics, I can't even get that right. I can't even count. You don't really need to know maths too much in digital forensics because you use a calculator. I think it's a big lot of you thinking like, why are we doing this? You just need to understand it because when you go to core, you need to explain it. So 16 times by 2 is 32. 32 times 2 is 64. And the next one is 128. And of course, all of these are currently set to off, so this byte would represent 0. Now, that means that if we add all these numbers up, we should get about 255, meaning that we can have 255 different results using this system. This allows us, but if we include the 0, 0, 0, 0, 0, 0, 0, actually we get 256 potential options, because of course we have all of these added together, which will give us 255. But also you have to count the zeros as being an option as well, meaning 256. This means that by using bytes, we can have up to 256 values. This is quite useful for us because that allows us to give us more room to maneuver. Now we've got more than 2 options when we do computer coding. Now, if you're saying, well, we need more than 256 options, then you can just use 2 bytes. And some systems will use 2 bytes. Because of course, if we have 2 bytes, then 128 times 2, then times that by 2, then times that by 2, and then you have loads and loads and loads. In fact, why not do this, shall we? So if we have more, yep, 1, 2, 3, 4, 5, 1, 2, 3, 4, 5, 6, 7, 8. So 128 times 2, I'm going to need a calculator for this, so I'm going to do this now. 128 times by 2 equals 256. So 256 as a potential option, times that by 2. 512. You start seeing these numbers come up a lot using the base 2 system. Times that by 2. 1024. Times that by 2. 2048. Times that by 2. You can see this is getting massive now. 4096. Times that by 2. 8192. Times that by 2. 16,384. And then times that by 2. 32,768. Now, if you were to add all these together, you would get a massive number, and that would mean that you would have lots and lots of options to pick from. And so that's how sort of computers work. If you need more more sort of information, then that's the 128, that's the 255, let's use another byte. If you need more than that, you need more space, let's use another byte. And keep on going and going and going until you've got enough bytes to allow yourself the information, to give enough space for the information. But fortunately for us, we don't need to use too much because we have a new fancier system in place in translating these bytes into sort of usable words and things and so forth. But that's the general idea of the base 2 system with bytes and bits. This allows us to keep going up, but normally you will see a byte, which will be sort of eight potential letter, or is it 8 numbers long, and a number of bytes will then give you a certain piece of information, or maybe just 1 byte, depending on how much space you need for that 1 piece of information. To put it into practice, let's give it a go. So let's go with a new one. So if we, oh no, let's go with new, and let's not save that. So let's go with 1 0 1 1 0 0. I'm doing 0 0 0 0 because I can't be asked to count that high. So with that, how do we work out the value here? Now, we're not going to go into the greater complexities of this yet, like little endian and big endian. We'll do that at another sort of video because it gets more complicated. It gets into a mind warp. But just to understand what this byte means. So if we take a look at this, this will be either a 0 or 1. So 1, 2, 4, 8, 16, 32, 64, 128. So we can see that that's been checked as off, so that's not 128. We can see 64 has been checked off, so not 64. You see that 32 has been checked off, so no 32 in there. 16 has been set off, that's not, but we have 8, 4, and 1. So I need to go 8 plus 4 plus 1. So 12, 13 is the value of that byte. So let me just do my counting again so I don't act like a complete mong. 8, 9, 10, 11, 12, 13. Yes. And that's how we can convert binary, it's basically zeros and ones, into decimal, which is 13. And of course, if we wanted to convert it back, so if we wanted to say convert 9 into binary, well, first we want to make our little table. So we do 128, 64, 32, 16, 8, 4, 2, and 1. That's a 1 there, don't worry about that. Come on, Mr. Krabs. I know it's late, but you need to be switching on, Big Shag. There we go. So we want to convert this decimal number 9 into binary, basically our zeros and ones. So how many 9s go into 128? None. So we go with 0. I do apologise, but that's a 9. I'll put a little 9 down here for you. There you go. Makes it look nice. How many 9s go into 64? 0. How many 9s go into 32? 0. How many 9s go into 16? 0. How many 9s go into 8? 1. That leaves us with 9 minus 8 equals 1. So we got 1 left. How many 1s go into 4? None. How many 1s go into 2? None. And how many 1s go into 1? 1. And so our binary value for the decimal number 9 is 0.0001001. Now you might be thinking, what's the point of all of this? It seems like a lot of crap going on with it I don't really care about. How do I find some evidence? Well, you need to understand how the evidence is stored, because if you can't translate what binary into decimal, then you won't know where perhaps a a file is located, or how big that file is, or you won't be able to identify it sort of the write time of it, because you won't be able to understand the sort of the binary values. Of course, the software will do it for you, but this is what the software is doing. It's effectively translating that binary into decimal, doing the system I've just outlined for you below. Now, what I'm going to show you now is something that may scare you, but don't worry. Okay, I'm just going to have to minimize something for a second because I did not prepare to get this far. So the next step is I'm going to open up HEX editor. I will go over some software for you at a later date, but for now we're going to do HXD. So HXD is basically a HEX editor. We'll go into HEX later, but for the most part, it's not too bad. Let me first find HXD first. Program data. I should have it somewhere. I get all this freeware, but I don't remember where I keep most of it half the time. So if I go to is it in here? No, it's not. I'll probably edit this part out, and if I forget to edit it, I'm sorry. Not hashcat. We'll do hashcat later. Should have it somewhere. There we go. And then I'm going to open up a file in it. So let's bring this up for you, and then we can do it from there. So let's open up a window capture for HXD. And let's see if I can show that for you. So what I've just opened up is a bit of software called HXD. If I just move over here, there we go. Now what this is called a HEX editor. Now we'll go into a bit more HEX shortly. It shouldn't be too complicated for you, but it will sort of explain my point. So I'm just going to load in a file for you. Let's go to my desktop. And I'm going to select it. Let's see, where's my test video? There we go. Now, I know what you're thinking. This is not binary. And you're right, it's not binary. Because binary is too long. Simple to get one value, you need 8 spaces long. So if you were to say get a picture and you were to print off its binary numbers, just a normal picture, a digital picture, you would probably use all the printer in your ink. You'd probably use all the ink in your printer, and would probably burn it out before you actually printed off all that binary data on your of that picture, and it would be a nightmare trying to do digital forensics with it. So what some clever guys did is they added another translation of binary into something called HEX. Now HEX is a base 16. 1, 2, 3, 4, 5, 6, 7, 8, 9. A, B, C, D, E, F. Yes, I think it's a base 16. Let me just search that and confirm that for you. I don't want to lie to you. Yeah, base 16. Which is a way of translating binary into another form of information. And for that, it uses 2 characters instead of 1. So you can see here the character up here, FF. That would be the equivalent of 1 byte. And I'll explain to you how it translates it later. But for now, my main effort will be to sort of show you more about this. And then, of course, the next one, D8, would be another byte. And then both together would be a word. But for the most part, you would have a byte for 1 here. Now, the HEX editor is going to show us the offset. We'll do more detail about offset later, but effectively where in the data or where in the file that piece of information is. Up here we have sort of going from 0 to 16, but of course it uses HEX, so 0 to 0F. And of course nearly everything in digital forensics starts at 0, because 0 is a value in itself. So when you're counting up to 16 or up to 8, you count from the 0. So 1, 2, 3, 4, 5, 6, 7, 8. There you go. So even though that says 07, actually that's 8 bytes. It's strange, but basically you get your head around it. So 00 is almost counts as 1, and then these counts as the final 16. And we'll go into more detail about explaining hex later, and we'll also explain what this on the right means, because you might be thinking, well, how is this helping me? What this doesn't make any sense. We'll do that shortly in the next video. But now, actually, we'll keep pushing through. You'll keep pushing through. I don't see why not. I know I said 15 minutes, but you get the drill. You know what I'm like with timings. So we're going to break it down some more so you can understand it. So once again, let's close this, minimize this. Let's do a little bit of writing. Yep. Okay. So we talked about the binary system and we talked about the decimal system, but hex is a base 16 system. Now hex allows us to see more bytes at once than if we use binary. If we use binary, it would take ages to look for anything and it'd be a nightmare. So hex effectively allows us to see more using less space. Now how hex converts binary data to hex, it's a pretty simple process. So if we take a look at, say, 1, 1, 1, 1, 1, 1, 1, 1. Here's our byte. Now, if you've been paying attention, or if your mind has melted at this stage, I don't blame you. When I first did it, my mind melted. You would see that this is 1, 2, 4, 8, 16, 32, 64, 128. So that would be 255, the largest number you can get in a single byte. Now, what hex can do is it can break it down even more. So what hex does is it effectively breaks a byte down into 4 bits. So 1, 1, 1, 1, 1, 1. And it breaks it down, so if we go and get my little rubber, it goes, aha, I'm going to break you down. So each half of that byte will have its own character value or number value. And then it will go 1, 2, 4, 8. 1, 2, 4. 1, 2, 3, 4, 5. Goodbye, you. You can probably tell I'm away with fairies. 1, 2, 4, and 8. There we are. And now if we count all these together, 8, 12, 13, 14, 15. 8, 12, 8, 9, 10, 11, 12, 13, 14, 15. But we count 0 as 1, so that would be up to a total of 16 potential values. But in total, it would be 15. But if we count the 0, it would be up to 16 potential values. And then it counts up. So what we do now is we start to add all these together. So 8, 9, 10, 11, 12, 13, 14, 15. Should it be 15? Well, you can only use one character in hex, so it can't be 15. Same here, you can only use one character in hex, so it can't be 15, because as you can see of hex, when I bring this bad boy up, let's see, can I bring it back up? There we go. You don't see any 15s here, do you? Because one byte can only use 2 characters, so you can't have 1515. It doesn't make any sense. So what people did, or what some clever people did, is they went from, instead of going 1 to 15, they went from 0 to 9, and then after 9, A to F. So A being 10, B being 11, C being 12, D being 13, E being 14, and F being 15. And so when we get all these characters together, we get 15. But of course, we can't have 2 characters, can we? So instead, once we get past the 9 point, we start using letters of the alphabet up to F. So 9, 10, 11, 12, 13, 14, 15, 9, A, B, C, D, E, F. And that becomes F. And on this side, it would be F as well. Meaning our hex value would be FF. So if we bring this back up again, we see our first characters are FF, meaning 15, 15, or which then if we translate back would be 1, 1, 1, 1, 1, 1, 1, 1, or 8 ones, meaning that is the fullest value. But let's take a look at the next one, D8. So if we go over here and do a new one, and we look at a hex value D8, well, we want to convert it back to binary. So how do we do this? Well, we split this into 2. See? So D, what is it? Well, 9, 10, 11, 12, 13, 14, 15, 9, A, B, C, D, D. So that is 10, 11, 12, 13. Let's confirm that again. Always double check with digital forensics. So 9, 10, 11, 12, 13, or 9, A, B, C, D, or 9, 10, 11, 12, 13. And then 8, that's being 8, so no issues there. So if we want to work this out, we want to split it in 2. And we go 8, 4, 2, and 1, and 8, 4, 2, and 1. So how many 8s go into 13? 1. So 13 minus 8 is 8, 9, 10, 11, 12, 13, 5. Confirm that. 8, 9, 10, 11, 12, 13 equals 5. How many 5s go into 4? 1. How many 1s go into 2? 0. How many 1s go into 1? 1. And then 8, 1 goes in, nothing left, so 0, 0, 0. And I forgot to show you that. Oops, here you go. Let's work it out again for you because I'm a bit of a potato. Okay, work it out again. Oh, you can work it out here. We'll work it out. So 13, 9, 10, 11, 12, 13, 9, A, B, C, D. D is 13. How many 13s go into 8? 1. That leaves 5 left. How many 5s go into 4? 1. That leaves 1 remaining. 0 because it's only 1. So 1 take away 2 can't be minus. So it's got to be 0. And then it goes 1 here. And then 8. Well, there's only 1 8. So that's fine. And the rest are zeros. Meaning that our binary value is 1 1 0 1 1 0 0 0. And then if we want to convert that even more into decimal, we simply have to we get rid of all of this. Okay. 128. Next is 64, 32, and 16. So convert to decimal. 8 plus 16. Bring up the calculator. 8 plus 16 plus 64 plus 128 equals 216. Now, if you want a cheat code, let me bring this up for you for your own reference. Can I bring it up for you? I'd like to bring it up for you. Let's see if I can bring it up. There we go, calculator. There we are. We can take a look over here. Now, this is quite a clever creature because you might be thinking, well, why am I doing all this maths? Well, you don't have to, but they like to know you know how a computer works in digital forensics. Don't know why to make you do a course to understand it. Perhaps they're thinking some solar eclipse is going to melt your mind and everything's going to go back to the Stone Age. But at the end of the day, if you can't be bothered to do all this counting, you just go to programmer. And there you go. We go to hex and we go D8. And 1, so its binary value is 1 1 0 1 1 0 0 0. Are we right? Are we right, ladies and gentlemen? Are we right? 1 1 0 1 1 0 0 0. Yes, we are. And its decimal value is 216. And I'll bring that back up for you. There you go. 216 decimal value, binary value 1101 1000. And that is how we translate it all together. And that is how computers work in sort of understanding the conversions between binary and decimal and hexadecimal. And do a final one just to sort of confirm your knowledge. If we go File, New, and we go with, I don't know, let's go with 92 as a decimal, and we want to turn it into hexadecimal. Well, let's work it out. So once again, let's break it down. 1 2 3 4 5 6 7 8. 1 2 8. 64. 32. 16. 8. 4. 2. And 1. 1 2 4 8. 1 2 3 4 5 6. So how many 92s go into here? None. How many 92s go into 64? 1. So we take away 64 and we get I'm just going to do my standard calculator now. 64 92 minus 64 equals 28. So we've got 28 left. Does 28 go into 32? No, it doesn't. Does 28 go into 16? Yes, it does. So minus 16, and we've got 12. So we've got 12 left as a value. So 12 left as a value. Does 12 go into 8? 8, 9, 10, 11, 12. Yes, it does. And that leaves 4 left. There we go. 0, 0. 0, 0, 1, 1, 1, 1. Or 0, 0, 1, 1, 1, 0, 1, 0. That's a 0. Sorry, boys. And if you want to confirm it, if you're going to be a bit crazy, a bit paranoid like I am, you simply add all the ones together. So 8 plus 4 plus 16 plus 64 equals 92. So we are correct here. But now we want to convert it to hex. So let's break it down even more. So let's break it down the middle. And then we have our 8, 4, 2, and 1, and our 8, 4, 2, and 1. So we've only got 2 of these ticked, so 4, 5. So 5 is the answer here. And because it's not 2, it's not 10, 11, 12, 13, 14, 15, it's just going to be 5. And then if we take a look over here, we have 8 and 4, that's 12. Where's my mouse gone? There it is. That's 12, but of course we can't use 2 numbers. So once again, 9, 10, 11, 12, 9, A, B, C. So it'd be 5C for our hexadecimal value, 5C. And if you want to confirm, bring up your calculator. Did I not show this to you? That's annoying. Oh, I just closed, that's why. If we take a look, so we want to do 92. Let's bring this up into our program view, and let's put our decimal value as 92. 5C is the hexadecimal value. Binary value is 0, 1, 0, 1, 1, 1, 0, 0. Did we get that right? Let's bring it up. 0, 1, 0, 1, 1, 1, 0, 0. 0, 1, 0, 1, 1, 1, 0, 0. Yep. And did we get our hexadecimal right? Yes, we did. So doing that all together, we can then eventually get the conversions between all these sort of values to make it make sense. And the logic for that is now we can understand what the computer is trying to show us, or what the software is trying to show us. If it's showing us FFFF, then if it's using 2 bytes, then it'd be a big number, or basically full space. Or if it's just FF, we know it's 255. If it's 0, 0, 0, 0, 0, you know, if it's 0, 0, if it's, you know, it basically allows us to translate it and understand what the computer is telling us when we look at this sort of binary data. So we can take a look at this, and now we can decipher what it's trying to tell us. Now, depending on the type of software, each area may have a different thing it's trying to tell us using these numbers, but at least we now have a vague idea about how these things work. Finally, we'll now talk about, well, how do we translate these into letters? So if I bring up back again the hex editor, where is the hex editor? Here it is. If I bring up the hex editor again, we can see on the right letters for these figures. So how is it that we are able to translate this hex into letters? And how that's done is something called the American Standard of Computing Interchange, I believe it's called, or ASCII. Many types of ASCII, but effectively it's a word table. And each word table has its corresponding value to it. So I don't know the values off by heart, you have to go online to find it. But simply put, if I was to just make one up, I don't know, FF would equal, let's see what the hex editor says, equals Y. Or 0, 0 would equal a full stop. And then, I don't know, Charlie 5 would equal an O, and Alpha 1 would equal a U. Of course, those aren't the actual values. You can find them online with ASCII. But simple terms is that what happens is the computer looks at these hex values and then looks at this chart of all these letters with their corresponding values in hex. Then it goes, okay, so I see an FF here, so that's going to be a Y. I then see a, so if we looked at this, say FF, Charlie 5, Alpha 1, 0, 0. The computer would look at this this jumble of hex, which we, of course, the average user wouldn't understand, and go with, okay, FF is Y. C5, look at my little chart, and that is an O. An A1 is a U. And a 0, 0 is a dot. So we see the letter U in our text file, but actually the data inside is this in hex. And then that is actually binary. And that is, of course, the long 0, 1, 0, 1, 0, 1, 0, 1 ones that ruin everyone's life and is very complex. So you see U, because that's the ASCII table translating it for you. Our forensic software will show it to us in hex, but in reality, it's those 0, 1, 0, 1, 0, 1s. Now, there is one issue with this, and that is there's only 256 different options you can use with 1 byte. And of course, there's a lot of different languages, which is not good. So what a new standard that came out was called Unicode, which uses 2 bytes. And of course, you've seen how big 2 bytes can get from this video. So it would be, I don't know, alpha 1 equals a weird hieroglyphic, I don't know, Korean symbol, something like that. And then a 1 byte for ASCII equals no. So A big thing that you need to understand is that ASCII would use 1 byte and Unicode will use 2. And sometimes the forensic software won't know the difference. So you might see something like D dot I dot D in ASCII. That's because it has converted to ASCII, but in reality, basically it's a Unicode format because it's using 2 bytes, but 1 byte didn't need to get used, so it becomes 00, and that might be, I don't know, F1. And so the word or the text could just be the letter did, and the space or the dot is just extra space. It's just like we didn't need to use that byte, so we're just going to leave it as a 00 or a dot. Quite complicated, but we'll go into more details about ASCII later, so don't get worried too much about it. If I bring up my HEX editor again, is that alive? Yeah, there we are. If I bring up my HEX editor again, you can see this is pretty much an ASCII because you can see no node. You can't see dots in between. You see, you're going to see first letter, second letter, third letter, fourth letter. Now, if it was say ASCII, we would see something like dot F, because that would use 2 bytes if that was Unicode. But because it's using ASCII, you only see this chap here. So it's quite important to understand how that translates. But if you want a simpler version of understanding this, I can give you a go at it. Let's bring up Paint again. Bring that back over here. I always forget to do this, but you'll get the general idea. I might go over it again if you guys get stuck. I need to get rid of my... There we go. Let's bring up Paint again. So we have binary. Actually, we have decimal values that then get converted to binary values, which are then presented to us for digital forensics as HEX. And for the normal person, for the normies, this is then translated to ASCII, or the sort of letter sheet or the code sheet, or Unicode. So the average person sees ASCII, the DFI sees HEX, the computer sees binary, and these binary values represent decimal values. We can do a little test of this later. I'll try and do my best to do a little test of this for you so it's easier to understand, but we'll go into more details at a later date. I'm aware that I've almost spoken for an hour now, but that's the general understanding. So this sort of video is to show you what a byte was, what a bit was, how the computer stores that information, and how that can be translated into real normal numbers or normal words or normal letters. Final test to demonstrate, I think, will be this chap. Okay, let's bring this back over to the right. There we are. So I want to change this. So I'm going to put the word in ASCII. Hello, my name is mildly startled. I put down in ASCII. That could just be a normal text file I use, and you can see that it is now being presented in HEX, when in reality I'm just writing new bytes to the machine. So we take a look at 68, that is H, and if we looked at the hexadecimal value, the binary value, that would be like 011010001. But I, the user, will see the letters when I open up Word or when I open up open up, I don't know, a TXT file, I'll see, hello, my name is mildly startled. But how it's being stored is in binary on the computer. And how I'm looking at it now is in HEX. Again, quite convoluted, quite complicated, but all you really need to know is computers store things in binary. Normally they use bytes as sort of the smallest sort of value for information, even though a byte is composed of bits, and these bytes can then be translated into hex values, and they can also be translated into letters. They can be translated into multiple things: letters, numbers, commas. So if I put a little comma in, can I put a little comma in? Let's put a little bracket. There you go, little bracket. If I put a little hash, a little tilde key. Let me put it down here. Put a little tilde key, put a little plus sign, put a little equal sign, put a little at sign, put a little C sign, put a little V sign. You get a general idea. But we'll go into more details on this later. Maybe I'll do a little demo next video. Anyway, that sort of concludes this video. And now we'll move on to something a bit more in depth than that. Okay, see you guys soon.